Welcome to Your Math Explained, where we make math simple and clear. My name is Angela, and in this video, we will talk about formally proving whether a function has an inverse or not, instead of just looking at a graph and deducing that it does. In previous videos, we introduced the idea of a one-to-one function, and we will continue to expand on that in this video. So let's dive straight in. We're going to start with the definition of a one-to-one function. So a function is one-to-one if each output is produced by exactly one input. So in mathematical notation, that means if we have f of a is equal to f of b, then we must have a is equal to b. So what this means is that if two outputs are equal, then the inputs that produce them must also be the same. So previously, we never actually used this definition, but what we did do was a horizontal line test. So let's take a look at how this actually relates to the horizontal line test. So let's say we have our parabola, and let's say that this here is where we have f of a is equal to f of b. So meaning we have two intersection points between the parabola and the dotted line. The y value of the first point is going to be f of a, and the y value of the second point is going to be f of b. And the x value of the first point is a, and the x value of the second point is b. So we said that a parabola does not pass the horizontal line test, which is why it's not one-to-one. And the reason is because we have the same output, which is f of a, is equal to f of b, but we have two different values for input. We have our a and we have our b, and they're different values. So what this means when we talk about one-to-one is if we have f of a is equal to f of b, then we cannot have another b value. This b value must actually be the same as the a value here. So the reason that we want to use this definition here is because we cannot reliably state that a graph is one-to-one, as we don't know what the behavior of the graph looks like towards the end. Meaning, we don't know if a graph is going to pass the horizontal line test without drawing the entire domain, which is impossible for most graphs. So therefore, the algebraic reasoning is more reliable. So we will use this definition to prove functions are one-to-one going forward. Okay, so let's take a look at this first example. We want to prove that this function f of x here is a one-to-one function. Okay, so using the definition above, that tells us if we have f of a is equal to f of b, then a must equal to b. So we will have f of a is equal to f of b. So substituting a into our function is going to give us 3a minus 4 over 2a plus 5. And that is going to be equal to substituting b into our function. So that'll be 3b minus 4 over 2b plus 5. Okay, next we're going to cross multiply. So the left side, we're going to get 3a minus 4 times 2b plus 5. And then the right-hand side, we're going to get 3b minus 4 times 2a plus 5. Now let's go ahead and distribute both sides. So the left-hand side, we're going to end up with 6ab plus 15a minus 8b minus 20. And that is going to be equal to, the right-hand side is going to be 6ab plus 15b minus 8a minus 20. Next, we're going to combine like terms. And that's going to give us 15a minus 8b is equal to 15b minus 8a. Now moving all the a's over to the left side and then all the b's over to the right side, we'll end up with 23a is equal to 23b, which means we must have a is equal to b. So here we've shown that by starting with f of a is equal to f of b, it leads us to a is equal to b. So therefore, it has satisfied the definition of a one-to-one function. So therefore, this function f of x here is one-to-one. Next, we're going to prove that this function g of x is not a one-to-one function. So what that means is if we start with g of a is equal to g of b, we won't be able to get to the result of a is equal to b. Okay, so let's start with setting g of a is equal to g of b first. So for that, we're going to get negative 2a squared minus 4a plus 3 is equal to negative 2b squared minus 4b plus 3. Okay, so note, we don't really have a way for us to combine like terms here because they're all different other than the 3. And we can't really deal with this algebraically easily at the moment. So what we're going to do is we're going to need to manipulate this equation first so that it's in a more friendly state. And we're going to do that by completing the square. So let's actually do that on the side. Let's perform completing the square on our function g of x. Okay, so g of x is equal to, so we're going to take out the negative 2. We get x squared plus 2x, and then we're going to add 1. And then we have our original plus 3, and then we're going to add 2 to cancel out the extra term that we added. So now we get this is negative 2 times x plus 1 squared plus 5. Okay, so this is g of x in another form. So let's go ahead and actually use that instead. So that means g of a is going to be negative 2 times a plus 1 squared plus 5. And that's equal to g of b, which is negative 2 times b plus 1 squared plus 5. And now we can cancel out the 5 and then cancel out the negative 2, and we end up with a plus 1 squared is equal to b plus 1 squared. So if we square root both sides, we actually end up with a plus 1 is equal to, and remember we have to have a plus or minus in front of our b plus 1. And the reasoning is because when we square both sides, one side could have been negative because once we square it, it becomes positive. So when you're square rooting both sides, we must always remember to take both the positive and the negative root. So now, solving for the two cases, we're going to end up with a is equal to b. So this is when a plus 1 is equal to b plus 1. And then the other case is when a plus 1 is equal to negative b plus 1, which means we get a is equal to negative b minus 2. So now we have arrived at two unique input values from the same output. So therefore, this function is not one-to-one. And now, since we've already gone this far, we might as well restrict the domain of this function so that it does have an inverse, meaning we're going to restrict the domain so that the function is one-to-one. And we're going to do that by using the vertex form equation that we've already written down here. So this is a parabola with the vertex at negative 1, 5. So meaning x is equal to negative 1 is our axis of symmetry. So since x is equal to negative 1, is our axis of symmetry, we just need to choose a domain of either x is less than or equal to -1, or x is greater than or equal to -1 to remove the symmetry. Each one of those cases will give us 1/2 of the parabola, and that is going to give us a function that is 1-to-1, resulting in an inverse function. So now let's do a recap of everything that we covered in this video. So first, we went over the definition of a 1-to-1 function, which is that if we have the same output, then it must come from the same input. And this connects to horizontal line test because it just means that when we draw a horizontal line, we cannot pass through two different points, which means that there would have been two different x values. We learned how to prove a function is 1-to-1 by starting from the definition and then manipulating it algebraically. And we also learned how to prove when a function is not 1-to-1 by the same method because we end up with two distinct inputs that can produce the same output. And then finally, we learned how to restrict the domain of a non-1-to-1 function so that it does become 1-to-1, which then allows us to find an inverse. And now it is your turn to give this a try. So here, you're asked to prove that the function f of x with this domain restriction of x is greater than 0 is 1-to-1. So leave your answer in the comments below and let us know if you'd like to see more advanced videos on inverse functions in the future. That's it for this video. If you found it helpful, remember to hit that like and subscribe. And if there's a topic you'd like us to cover, make sure to drop it in the comments.